prove the second part of the fundamental theorem of calculus. That is that these area-as-you-go functions are antiderivatives. So once again, we have an if-then construction. If f is continuous on the closed bounded interval ab, then the function capital F, defined as this area-as-you-go, is differentiable on the open interval ab, and the derivative of this area-as-you-go function gets you right back to f of x. In other words, these area-as-you-go functions are, or in other words, integrals are antiderivatives. So we had a nice geometric argument we talked about in section 5.3, but to actually prove it a little more precisely, we're going to use the mean value theorem we learned in section 5.4. So here's the proof of that. So we're going to assume the if part. So we're going to assume f is continuous on the interval ab, and we're going to define capital F of x to be the integral from a to x f of little t dt for some x between a and b. So I want to calculate the derivative of capital F. And this goes back to the definition of derivative we had many weeks ago. Namely, the limit as h goes to 0 of capital F of x plus h minus capital F of x divided by h. So now what we want to do is we want to go in and look at the definition of capital F of x and simplify this numerator. So capital F of x plus h means everywhere I see an x in my definition of the function, I'm going to replace it with the quantity x plus h. So when you look at f of capital X, the only place x shows up is in the upper limit of the integral here. So that's the integral from a to x plus h little f of t dt. And capital F of x is the integral from a to x little f of t dt. And so if I look at capital F of x plus h minus capital F of x, this is the integral from a to x plus h little f of t dt minus the integral from a to x little f of t dt. So geometrically, this is what we have going on. So we're integrating out to x plus h, and we're subtracting what we integrate out with respect to x. So what's going to be left is this little slice from x to x plus h. So we can formally work this through with the properties that we talked about in section 5.2. So if I look here, I can reverse the order of the integration to take care of that negative. So I could rewrite this as the integral from a to x plus h little f of t dt plus the integral, instead of going from a to x, I'll go x to a f of t dt. So using the reversal property. And now I'm integrating from x to a f of t dt, and then picking up a to x plus h. And so then I would write this as the integral from x to x plus h f of t dt. And that's what's going on here in the picture, is I just have the integral from x to x plus h. Oh, and here comes the cat to chime in. All right. Now, this is where the mean value theorem comes into play, because when I integrate from x to x plus h f of t dt, I can hit this with the mean value theorem for definite integrals. Since little f is continuous, I know that I can rewrite this integral. Well, let's back up a little bit. I'm not quite done yet. Let's go back here. So that's what's in the numerator. And then I'm dividing this by h. So if I go back over here, I'm going to put if I divide this by h, then the mean value theorem for definite integrals says that this is going to be equal to, well, this is the average value of f from x to x plus h. This is going to equal to some little f of c, where c is between x and x plus h. So that's our mean value theorem. For integrals. That's equal to the f of c. So, going back to this limit here, my derivative is the limit. This is just the limit as h goes to 0 of little f of c. Now, since c is somewhere between x plus h and x, as h goes to 0, that's going to force c to go to x. So this is going to be the limit as c goes to x of f of c. And since little f is continuous, that's just going to get me back to f of x. And so the mean value theorem for definite integrals makes that argument, that little hand-wavy geometric argument we talked about in class, a little more precise. And so there it is. That's the fundamental theorem, part 2.